if you want reliable, high-accuracy drone photogrammetry. You already know there's no way around it. You need ground control points. But how many do you actually need? Why is your elevation data always slightly off? And what is the absolute fastest way to mark hundreds of ground control points without losing your mind? Today, I'm breaking down the exact workflow that guarantees survey-grade accuracy. If you find it helpful, please smash that like button and subscribe, and stick around. Leaving a comment below on what tutorial you'd like to see next could win you a 1-year MipMap Pro license worth $799. The comment with the most likes in the next 72 hours takes it. Let's dive in. First, how many ground control points do you actually need? For drones using regular GPS, the most critical function of GCPs is transfer your model's coordinate system into an accurate coordinate system. Mathematically speaking, you only need 3 non-collinear points provide the 7 parameters needed to lock your 3D model into the ground control points' coordinate system. Let's break it down. With just 1 control point, the model can still spin around it. With 2, it rotates on the axis between them. You need exactly 3 control points to fully lock your 3D scene down. But here's the catch. That just handles the coordinates. If you only place 3 points, your model is still vulnerable to distortion, specifically the bowl effect, and scale errors on your z-axis. If you're an experienced drone mapper, you know this headache. Imagine surveying a perfectly flat field, but in your 3D model, the ground curves up or down like a giant salad bowl. This is a classic issue in nadir, or top-down mapping. You can think of this distortion like the surface of a giant sphere. Even if you pin down 3 different control points, the center and radius of that sphere can still shift, warping the entire model. And if you're flying nadir and your 3 control points are on the exact same flat horizontal plane, you risk massive scale errors on your z-axis. Let me explain why. Photogrammetry utilizes the pinhole camera model to mathematically represent the imaging process. The most fundamental and critical principle of this model is that the object point, the image point, and the optical center of the camera all lie on a single straight line. If all your photos face the exact same direction, the photogrammetry's self-calibration algorithm struggles to pinpoint the precise focal length. This creates depth ambiguity, making it impossible for the software to decide the exact elevation. In the example here, the elevation of the model will be compressed, centered on the elevation where the ground control point is located. Let's take a look at the scenario where oblique imagery is involved. If the object's elevation and focal length are estimated incorrectly, its position in the oblique view will shift. The reconstruction algorithm can detect this error and thus uniquely determine the object's true elevation. To break this uncertainty, you must introduce oblique imagery or use GCPs with significant height differences. And this is exactly how DJI's elevation optimization feature works. After finishing the top-down capture, the drone automatically snaps extra shots at a 45-degree angle toward the center of the site. Another golden rule for ground control point placement is maximum coverage. For standard rectangular survey areas, place 1 control point near each of the 4 corners, plus 1 right in the center, to prevent the middle from warping. However, ground control points are part of the calculation. They can't be both the athlete and the referee. A low error on your ground control points doesn't automatically mean your final map is perfect. To truly verify your accuracy, you need to add independent checkpoints to act as the final judge of your project's quality. What about the pattern of the GCP target? The absolute best options are dedicated black and white checkerboard mats. For sites you survey frequently, use high-visibility spray paint to mark clear checkerboards or large crosshairs on flat ground. If your site already has clear corners, like painted road markings, you can use those. Just meticulously record which corner you surveyed so you don't click the wrong one later. Please note that. Never use the center of a circle. In oblique shots, a circle becomes an ellipse, and the optical center in the photo is not the true physical center on the ground. Also, keep targets away from tree canopies, high walls, or tall buildings. These block your RTK satellite signals and cast shadows that will hide your targets in the photos. Field work might wear out your legs, but the office work shouldn't wear down your spirit. Efficiency is everything, and today we're demonstrating how to achieve that using MipMap software. Marking ground control points by manually clicking the exact center of a target in dozens of photos is notoriously tedious. But if you follow the best processing workflow, you can cut this time down to a fraction. If the images contain RTK position, GCP marking would be super easy. After creating the task, import the images captured by the drone. Select the ultra-high precision level and first turn off both the 2D output switch and the 3D output switch. Click the Start AT button to calculate the precise camera parameters. This is blazing fast. For a few hundred photos, it takes just a couple of minutes. Once aerial triangulation is complete, drag and rotate the scene to check for any cameras with abnormal positions. Then open the GCP settings. Import your GCP file. Set the correct coordinate system. You can search for the corresponding geographic coordinates by entering the EPSG code, or by entering the coordinate name. Hit Confirm. Verify your columns, set the names of the columns corresponding to the data, and hit Confirm. Your imported GCPs will now appear overlaid right on the sparse point cloud. Let's look at the ground control points setting interface. Top right is your point cloud. Bottom right is your ground control points list. Click a point, and the left panel instantly populates with thumbnails of every photo that sees that point, sorted by visibility. Click an image to enter the marking window. The blue circle is where the software predicts the ground control point is located. Scroll the mouse wheel upward to zoom in the image for more precise GCP marking. Click the left mouse button to mark the position of the GCP in the image. After marking 2 to 3 images, MipMap's prediction will become ultra precise. Most of the time, you just hit Confirm and use the right arrow key to fly through the rest of the images. During the marking process, if you accidentally mark an incorrect position, the software will show a corresponding warning and display the marking error. If you want to delete the markers of a ground control point across all images, click the Delete button in the top left corner while the corresponding point is selected. Repeat the marking process for all ground control points. After marking all points, determine which points will be used as control point in the calculation, and which ones will serve as checkpoint for accuracy verification. This is in accordance with the horizontal distribution principle of control points mentioned in our previous tutorial, and ensures that the elevation of at least one control point differs significantly from that of the other control points. Considering only the factor of control point position distribution, placing one control point in the absolute center of the survey area is the optimal method. However, if the corresponding survey area requires long-term repeated mapping, you have to consider the stability of the control points. In other words, control points and checkpoints should not be selected in areas that undergo frequent changes due to construction. Therefore, we chose an area slightly off-center. Ground control points marking has been completed. Click the aerial triangulation button in the bottom left corner to start the optimization. Now, what if your drone didn't have RTK? You're using standard GPS with meter level drift. Here, we added a 10-meter elevation offset to all ground control point for demonstration. I will speed up this section to repeat the previous GCP import operation. After importing the off-seated ground control points, they might look like they're floating way above or below the point cloud. To solve this problem, we first identified 3 well-distributed control point points in the survey area to align the image coordinate system with the GCP coordinate system. In the crowned control point marking viewer, the predicted crosshair might be hopelessly lost off-screen. Don't panic. After you mark the same crowned control point in 2 photos, the software can predict the position of this crowned control point in the remaining images fairly accurately. Repeat the same operation for the other 2 points. Once those 3 points are marked, turn off the position constraints and click Optimize to run a bundle adjustment. In those off-screen predictions, they've all been pulled right back onto the targets. From there, you can switch back to the Fastlane RTK workflow and enjoy that semi-automatic snapping. Let's speed up this section. Why does this work? Like we said earlier, 3 points are exactly what it takes to align the coordinate systems. Once the optimization finishes, your crowned control points will perfectly hug the terrain. Let's wrap this up. Built-in RTK is never an excuse to skip ground control points if you want survey-grade accuracy. Stick to the 4 corners plus center rule, and in the office, use MipMaps, predictive snapping, and the 3-point pre-optimization trick to save yourself from the endless abyss of manual marking. That completes our ultimate masterclass on ground control points. If you got value out of this deep dive, please hit that like button, subscribe. If you have questions about MipMap 3D reconstruction software or aerial mapping, drop a comment below. See you in the next video.